Hello and welcome to last review video. This week we'll be talking about flash memories. Now, flash memories, they exist on the bottom tier of the memory hierarchy. Now, this means that they have a much more slower speed compared to other top tier devices such as CPUs or dynamic RAMs. But however, they possess a gigantic memory space to cover those slow operations. Let's talk about the structures of flash memories. Now, the flash memory structure is very simple. It's the normal MOSFET structure, but however, there's a one more gate stack or charge trap layer depending on the device operation. Now, the whole ordeal of the flash memory is to utilize these charge trap layers. Now, how do we use it? The first It is called a write operation or program operation. Now, what we can do is we could give a positive bias on the gate, just like a normal MOSFET device. And with this positive charge, the electrons on the bottom of the channel gets lured into the floating gate or the charge trap layer by a Fowler-Norden FN tunneling. And with this newly formed electron on the gate stack, we can determine that if either the flash memory device has data or empty. And this op- and the operation to check the data is a read operation. In read operation, we just give our predetermined bias on the flash memory, and when it returns a certain level of current or the under level of the current, we could easily know the state of the flash memory device, whether the device is stored or empty. The final operation I will explain is the erase operation, and this operation is the reverse of the write or program operation, that we just give a positive bias on the body to rescue our electrons, which was trapped in the floating gate or the nitride oxide. The next I'll explain is the two different kinds of flash memories. The first is the NOR flash memory, and second is the NAND flash memory. Now, in the market, the NAND is more popular, and that's because the NAND has way more room for integration. Because the NOR memory, you could only store one cell per one cell. But however, in the NAND, you can just line up the whole gates and achieve a maximum level of integration. Now, speaking of integration, much like our MOSFETs and other devices, then flash memories too have a innovation for integration. And the first innovation I would like to explain is the multi-level cells, MLCs to be short. And this is a much more different. Rather than giving a change in structure, we give a change in programming. Rather than have a one distinct threshold voltage level, we set up a bunch of threshold levels, such as we give a 8 different threshold levels, and in the QLC we give a 16 distinct levels to achieve a more diverse memory capabilities. But however, there's a downside. As we all previously know, there's a certain device variation or process variation on the device. So, in order to utilize our more effective layers of multi-layers of bits, we have to precise our device control and process flows. The last integration scheme is the change of structure. Now, as we learned from previous lectures, we used to learn from planar devices into 3D devices. Not the same thing applies to the flash memories. We used to have a planar two-dimensional just lines of NAND gates. But however, from now we just make it vertical and stand up upright. Hence the name VNAND or 3D NANDs. Uh, that will be it because it's 5 minutes. And thank you for listening. This has been Myung Kim.